Well, thank you, Gary.
It's up to you.
All right. And yeah, we're very happy to have this be completely interactive, so feel free to ask questions throughout the talk. So, well, Gary's mostly given the whole introduction. I'm not going to talk a lot about the Berkeley Water Center in this talk. I'm going to talk about a project that we're doing within the Berkeley Water Center with Microsoft and building some real capabilities. And so just to give you an outline of the talk, I'm going to talk a little bit about the landscape that we're dealing with, the sort of problem, and this fact that we've got a lot of data and we need some ways of starting to deal with it. What we've been building is a science data server. You'll have noticed maybe that we've called it both service and server. That's still trying to figure out what the right name is. It probably should have been server. So you'll see in these slides it's called a server. But you're welcome to debate that point once you hear more about it. And talk a little bit about what the next generation capabilities we want to build are and some of the research issues that are brought up by trying to build this system and give a conclusion. So first off, what we've seen in the science area is a large introduction, or an introduction of a large number of data archives. Right? There's an unprecedented amount of data that's available today, and there's been a real push at the funding agencies and at a lot of the government agencies to start to build data archives, to make data accessible to the broad science community. Right? So we've got, I mean, this is just a small fraction of the number of data archives that are out there now. The USGS folks, the Quasi folks, Flux, which we'll mention a lot more about, a lot of the climate data sets. I mean, there's really an amazing amount of data now available out there on the web through these various portals for scientists to be able to get access to. And so what we see happening today in terms of how people deal with that data is typically you'll see that people do go to those data archives, download the data that they need. They typically, though, that's not all the data they need, right? Typically, that's just the beginning. I mean, that's sort of the framework within which they're going to do their analysis, and it provides a component of what they need. But typically, they're also going to need a lot of local measurements as well that are going to augment that data and provide some of the particular science values that they need. Often, they're going to couple this with models and look at some of the model outputs in comparison to the data, or to use that to understand the data better. And what you see today, typically, in these environments is that each of the scientists in a group have their own data collection that they're working with. And so each of them have gone and downloaded some subset of data from the various archives, have done some number of measurements, have run some number of models, and have some subset of that collection of data on their individual desktop or on their individual server, and they're then working with that data. Now, what you actually, in fact, see if you then go in and talk to each of those individual people, you'll find that it can be that maybe they each have what appears to be the same data set, but in fact, they've gotten it from slightly different locations or at slightly different times, so that in fact, even the data sets they've gotten from the archives aren't necessarily the same that each of them are working with. Often they've done individualized calibrations to the measurements that they've taken, done particular tweaks with the models, and you find that very quickly each of those scientists has a completely different data set that they're working with. And at least in our case, what we realized is they didn't even realize they were each working with different data. They were all under the impression, because they were all pulling from the same places, that they had the same data. And so in our case, what we're working with is the Flux data. Just to give you a brief overview of what Flux looks like and what they're trying to do with Flux to set the stage, basically it's a set of towers. Right? There's a particularly tall one of the towers. There's a lot of ground measurements as well. What they're primarily trying to do is measure carbon flux. So there's 149 of these sites across the Americas. What you saw in the graphic was basically a rough location of where these all are. And The idea is to have each of these towers report a minimum required set of values, and then whatever else they want to report, right? And the idea then is to be able to bring together the fact that they have all these towers doing common reporting and actually be able to start to do regional science across these towers, start to understand ecosystems, start to understand things at a larger scale than just any one tower. So what they've done is they've brought together this community of these towers. They've published the data. Oak Ridge National Laboratory is hosting the database that has all the Ameriflex data. And at this point in time, they have about 150 million data points. The data starts as early as 1991. The reality is from 91 to 94, there's only one site reporting. So starting with about 1995, there start to be more and more sites. Really about 2000, you start to see a larger amount of sites and starting to see the network starting to ramp up. When Catherine shows you some of the data that she's got, you'll actually see that directly in the data. So there's the website if you're curious more about Ameriflux. What I want to give you a brief overview, not being an environmental scientist, this will only be the cartoon version of what they're trying to do, but I want to give you some idea of what's going on here because it'll frame the issues in a way that allows you to see sort of why there's issues with trying to use this data and why it's particularly difficult, but I think it's consistent across a broad range of particularly the life sciences. Basically, what they're trying to understand is the carbon flux through the ecosystem, right? So understand what happens in terms of the balance of the carbon, as photosynthesis occurs on the vegetation, and the various, the trees, the ground, everything respirates back. What is that balance, and what are the factors that affect that, right? Why is that amount of carbon taken up by this particular ecosystem? Is rain the factor? Is it the amount of sunlight they had? What are those factors that created that? And so they need to understand all the terms in this equation to start to understand what is that balance, right? So this is just from Dennis Baldacchi's lecture, actually it's his undergrad version. Well, it's in his undergrad talks, but it's also in some of the lectures he gives. So this is just a cartoon from Dennis. And so just to give some brief examples of the types of things they want to understand by looking at these Ameriflex towers, I already mentioned they want to understand the carbon exchange within the system. They want to understand the climate change aspects, right? What's happening in terms of climate change when the springs get earlier? What happens there? I mean, does it change when the leaves come out? Does it change how many leaves you have? Does it change how much photosynthesis occurs? Does it change the duration of all of that, right? Does it, is it the case, right? From my simplistic view, and Dennis will probably correct me if I'm completely wrong, but from my simplistic view, you might think, well, there's going to be more CO2 in the atmosphere from the global warming aspects. Well, isn't the Earth just going to get greener and take up more CO2 because now the plants have more food, therefore there'll be more plants, right? That would be, at least from my perspective, one of the simple questions you'd immediately ask. Well, with these sort of towers, you can start to understand those sorts of things. So one of the studies they've particularly done is looking at what happens in early spring and looking at does it make the growing season longer, or does it in fact mean that everything dies off early in the summer and in fact you have a long drought sort of environment. They want to understand how different ecosystems and the latitude plays into all of this, right? Because ideally you want to be able to have a model of exactly what happens in terms of carbon uptake for each ecosystem and exactly what are the factors that affect it. Because if you could get to that point, you could start to predict what happens. There's also different studies to look at the effects of various pollution sources and what happens in terms of the carbon exchange when you have different pollution sources. I mean, just one example would be airplanes, right? And trying to look at, at different instances like 9/11 when the airplanes were all grounded, can we see a difference in the carbon uptake? Right? Things like that. So the problem, though, is that these are environmental measurements. They're really hard to make. Measuring all of those, the variables that are in that equation is not trivial. The instruments are very sensitive, and these processes are hard to catch in some respects. So what happens is you get a lot of gaps in the data, and there are a variety of reasons. They're everything from that, well, at night everything's just too quiet and it's below the sensitivity of the instruments, so I have no data from it, some nights, to, well, the bird pooped on the thing. And these are fairly remote towers in many cases, and I just can't go out there every day because the bird pooped. So you could have a long period where, in fact, the data you're getting is either just wrong because it's in fact reading a bird poop or a bird sitting on the sensor, or anything like that, to the cases where, in fact, it's environmental conditions that have caused something. Like, it's very high winds, right? If I'm measuring carbon flux, it's going to be a little bit difficult at extremely high wind conditions to measure vertical carbon flux if everything's going horizontal. So there's also many measurements that they need for these equations that are exceedingly hard to make, right? So leaf area index is basically a measure of exactly how much leaf area is there in this area. Well, the easiest way to measure it is chop down the tree and measure every leaf. Not exactly a straightforward or renewable method. So you want to avoid that. So then it's all by doing measurements that give you an idea of how much leaf area there is. So there's things like using the satellite measurements that measure how much green they see. And there's ways of starting to run instruments underneath the canopy to look at how much light filters through, and then use some equations to figure out how much leaf area that must be. So you get sort of the point with these measurements. I mean, the wood respiration, soil respiration, same thing, is that many of these end up being things that you take on an infrequent basis in the measurement at the measurement site, and they're indications and not necessarily exact values, right? They might be a range. They might be there might be multiple measurements via different techniques that could then be combined to get a more exact attempt at the measurement. There's a whole variety of types of measurements that come in this sort of arena. Also, with the Ameriflux, you're looking at a very localized measurement, right? This is just a tower. So it's about a 1 kilometer square area that it's really measuring. And you really don't have measurements about what's happening outside of that space. And this is very much an evolving science of starting to understand the ecosystem exchange and the carbon flux. And what you find as well is that in each of these towers, there's a local PI who runs that tower, who has decided exactly what instruments they need to measure this, and exactly what is the best method to do the measurements, and feels very strongly, now not being able to, I don't have any judgment on this, but it's very clear that they each feel very strongly that, in fact, they are one of the only people who can interpret their measurements correctly and make sure that all of the calculations take into account all of the factors, right? Because, and these are a broad range of ecosystems. They're everything from forests to grasslands to croplands, and there are a large range of factors in here. And when you start trying to come up with what is that net ecosystem exchange, it does take a lot of local knowledge. So I'm pretty sure it's not a fallacy there. But also, the reason why these PIs have gotten in this game, right? Why have they joined this network? Obviously, part of it's to get funding. We all live with that reality of that. We join projects because it's to get funding. But the other reality is they've got a particular science goal that they're after with their tower, and they have particular questions they want to answer. And those are not necessarily tied to the 22 variables that are the core variables. They may be a completely different question that they want to answer, and they need a tower. The way they're going to get funding is join the Ameriflex network and be part of this and do all the core measurements as well as their own, right? And so what you'll see as well within the data is that, in fact, there's some, well, Catherine will show it very well. But I'm sort of setting up some of Catherine's plots, because the reality is when you look at these plots, this will pop out immediately, that some of these PIs have a completely different science agenda that the tower is built for, or at least additional science agenda besides those core variables. So the other piece of it, besides the towers themselves, and I've sort of explained some of this, but they need a broad range of other measurements to start to interpret what's going on with the Ameriflex data. Right? If I want to be able to look across sites, I need some of the remote sensing data, things like the MODIS data sets, which are satellite data, to be able to start to pull together what's happening outside of my 1 square kilometer and between this 1 square kilometer and that tower way over there. Right? And starting to try to understand how those processes are happening. There's a lot of microclimate data that comes out of each of the towers, but ideally you'd like to be able to tie that then to the broader climate data from NOAA and other places like that have a more continuous data set. Same with the soils data. There's a broad range of other databases that you want to bring to bear when you're asking the science question. Right? Starting with that Ameriflex data is a fantastic starting point, but when I get there I go, oh, well, I need all this other data, right? That's immediately the problem. And that's what leads to the slide where I had, data going everywhere, in fact, out to each person's laptop or desktop. And so the project that we're building, and I'm going to turn it over to Catherine now, is really a data server that's to serve these small collaboration groups and give them a way to be able to bring all this data in that they need to do their science, but provide them the underlying infrastructure to do that well, and to provide them something where they can have some assurance that they know what data they have and they know how they got it and who's done what to it. So let me turn this over to Catherine.
Before you go there, just
yeah.
So whose funding is driving the uniformity of the core data elements?
Of the Ameriflex?
Yeah.
The Ameriflex is DOE funded, right?
It's a combination of funding. There's DOE funding, there's NSF funding. I think there's not a funding that's driving the core, but rather the joint mission to really look at what is the interaction between the small scale carbon flux and the larger scale. Right? There's actually a real scientific thing that people are bonding together to try and do, in addition to the specific research agendas.
Right, and so those 22 variables are what they consider to be core to being able to put together that equation and do the net ecosystem exchange and some of those.
Okay. Well, let's take a look at what we're really kind of trying to build here. So one of the things that we kind of did was focus on what problem we're really trying to solve. Well, the goals of what we're trying to do, there are really three. First, to provide a repository. One of the things we've noticed is that people have data in various places. All right? I know I don't do that. I know you don't do that. But real people keep their data everywhere. Right? I have this on my laptop. Oh, yeah, well, I've got it on this disk over here, except I've got it on the file server over here, except, well, I sort of have this copy over here. And then there's, of course, the little napkins that I kept from conferences. Right? So first of all, providing a place that's simple to put stuff, so you want to put stuff, and tracks where you got it. Oh, I got that from a cocktail napkin. I got that from talking to Deb. Second, provide a way that scientists can simply interact with the data. Basically automating some of that download so that when the data changes on one of the interactive sites, you get the new data, or you don't get the new data, or you at least know that data has changed. We noticed that scientists are spending a lot of time going out to these sites and getting the data I want, finding it, keeping it, and constantly going to go get it. after you've made a change to the data by one of these private recalibrations, do you have to rechange that again? How do you know what's changed? So sort of getting some of that, just simplifying it. So it shouldn't be a big issue. One of the first scientists we talked to was one of Dennis's postdoc, who's now at UC Davis. He had spent 3 months assembling a subset of the Ameriflux data set. Okay? 3 months. That's way too hard. Okay? It's computer science that can make that a little bit easier. And lastly, we wanted to support some basic analyses. So I call it sort of browse for science. Okay? It's not really big science. It's not really modeling. But being able to get a sense of what the data looks like, what really could go on, what if, was there any change around September 11th? Well, you shouldn't have to go through a large mechanism or a large analysis. A fast browse should help. That's wrong key. What aren't we doing? I always kind of do both. We're not replacing some of the internet sites. There's a lot of work going on, as Deb mentioned, with both national organizations like NOAA and NASA, as well as small collaborations like the Ameriflux collaboration, assembling data and making it available on the web. We don't really want to kind of try and replace that. There's technology in common, but the problems and the scenarios and the issues around doing a deployment are very different. We also want to not really get into the whole business of complex modeling and statistical analysis. There's a lot of tools out there for doing statistical analysis. S+, SAS are two that we've encountered, ArcGIS on the geographical side. Simply redoing those tools, there's no gain there. In addition, scientists tend to choose the tool that they like. Why use a tool that's the same but different? I don't know about you, I hate it when we change stuff, right? And I can't find the option I was using last time. So that really what we're doing is building only a part of what would be a wider laboratory information management system, or LIMS. It's one of those kind of buzzwords you hear from time to time. And lastly, it's not a goal really to develop some new standard schema or control vocabulary. Again, there's a lot of work going on these days in various places trying to work out interchange standards for data. NetCDF is a good example of that. Or control vocabulary. What is discharge? What is carbon flux? What is, okay, there's a lot of people, again, working on those things. We expect to be able to leverage that. Partly, one of the things that's going on, I think, as well in environmental data is that since you're picking data from here, here, and here, you're going to have to accommodate multiple naming conventions. If you're taking data from an EPA site, it's going to be different than if you take data from a USGS site. So what does it do? Well, first of all, you want to be able to add new data and add new metadata. Now, Deb was talking earlier about the kinds of information, field measurements like leaf area index. That's what I'm going to call metadata. It's not sort of taken at a regular basis as the half-hour tower measurements. It's taken every now and then. Okay. Additionally, you want to be able to derive new measurements. They're very simple calculations very often that occur. Cumulative precipitation. You may want to compute relative humidity from the constituent elements. So being able to compute the simple things, again, this idea of reducing the barrier to entry, reducing the handling, making things simple. We have to support editing because, as Deb mentioned, individual researchers apply individual recalibration judgment to data. Oh, I know that that tower always is off by 10%. Okay? And that really is an editing function. It's a scientist interacting with the data, sometimes as a whole, sometimes as an individual datum piece. Okay? And pushing the data back into the repository. Gap filling, it turns out to be another editing thing. It was a learning for me. I thought initially of gap fill as just filling in holes. It turns out some of the algorithms actually occasionally replace because you're doing a real spectral analysis, power spectrum kind of thing. Sharing, making the latest data available rapidly. When new data arrives from one of the internet websites, it should be able to be seen early. Even though it may not have really been looked at carefully, but being able to make data available to members of the collaborating group so they can all look at it. Does that look good? Do we want it? I don't know. Looks good to me. Then private analyses. MyDB is kind of a word that the Sloan Sky server started talking about. It's the private data. There's the data that we're all sharing, but then there's the data that I'm using for this paper right now. And I know for this paper, I'm going to change this algorithm, and this algorithm. I'm not going to use the standard gap fill algorithm because I'm going to use this other thing over here. So it allows the same interaction, but with a private set. Okay? And lastly, providing the versioning and provenance. Most of the sets out there do at best a very crude versioning, as of the end of the water year. What we're noticing with a lot of this data is it's much more dynamic. And remembering, oh yeah, I added that calibration, or oh yeah, this is different. And being able to compare this gap fill algorithm or that gap fill algorithm turns out to be very important for the science. So baking in an idea of versioning and making it simple to use was something that we felt was very important. So what does it look like? Well, there's a lot of data analysis tools. Right? There's desktop tools, simple web plots. For those of you that haven't looked lately, there's easily 10, or I actually found a dozen, kind of web plots that can plot 1,000 points. Okay? Java tools, this, that, and the other thing. They're all out there. We built something over the summer that I've dubbed Big Plot. It's specifically targeted for plotting roughly 1 million points. Million is actually a hard number, it turns out, both in terms of simply getting it and also being able to render. So we're playing with that, kind of trying to understand how we might do some very simple viewing of very large data sets. Kind of a little research aspect. We standardize on flat file import and export. It's what everybody's using. Okay? So that editing function is really about getting a flat file, changing it, and pushing it back. Makes it very simple workflow. And of course, computational models for more serious analyses and simulations. We organize the server really as collections of databases and collections of data cubes, and kind of the middleware around it. We hold all the data and all the metadata, all that descriptive stuff, in a database, standard relational database stuff. While I'm showing various data sets, whether that's one big database or lots of little databases, that's kind of deployment, and we're still working out sort of what the simplest way is. From a point of view of a user, there are multiple databases. They all look independent. We always stage data on the way in. As Deb was explaining, this data arrives dirty, okay? And somebody has to look at it kind of and check. We've been now scraping the Ameriflux website. We've done it 4 times, Deb, or 3 times?
Yeah, I think I'd call it 3.
I call it 3. That 3 is good. Every time we scraped it, the data's changed. Every time we scraped it, columns headings have changed. We went from single quotes to double quotes. We picked up numbers that were outside the range of single precision floating point. Okay, so this stuff always arrives dirty, and that's after it's clean, people. Okay, this is not as it arrives from the investigator. In talking with the folks at Oak Ridge, as it arrives from the investigator, all bets are off. Right. So staging is important. Kind of think about it as quarantine. And the MyDB. What we realized is there's really 3 versions of the data that are really handy. The latest, greatest. Whatever's come in latest, whatever is latest downloaded, it's gone through staging, but after that. And last known good, the stuff that we all want to use. What we've seen as we've talked to a lot of these smaller collaborations, they all kind of know. That's the set we all use now. It's on that file share over there, and that's the stuff. Oh, well, yeah, this stuff. No. That's the stuff we all use. And lastly, the older archive. Don't throw anything away. Data cubes. A data cube is, and we're using a term very, very kind of computer science pure here. It's a special kind of database, specifically optimized for database mining. Commonly used in the commercial world for things like looking at Oreos and milk, cigarettes, you know, kind of tracking sales. If you ever wonder how Walmart or one of your other, or Safeway, for example, decides to give you that coupon, well, that's database mining. Cubes are really good at doing simple data aggregations, okay? Sums, mins, max. They're pre-computed. So while you could write the SQL to do all of the things that a database cube could do, it's optimizing and simplifying a lot of the SQL that you'd have to write, okay? There's a query language dedicated called MDX, which is very similar to the query language used for SQL. It's optimized for mining, for finding measurements on columns and rows, okay? Think of the output of a data cube always as some sort of spreadsheet, rows, columns, and metrics. The integration with client tools is still in a state of flux. Cubes coming down market outside of very, very high-end database deployments is relatively new. And so the wealth of desktop tools that you find that integrate with SQL are still really emerging. It turns out Excel is one. There's a couple other ones that are currently being used in commercial mining. I'll show you some of the output for some of those that we've been playing. But Excel turns out to be kind of really pretty straightforward. So let's look at some data. Here's a little Excel plot that shows when the towers report data over years. Okay? And Deb was saying towers come and go. Something about funding cycles being 4 years. Okay? And there's then, of course, field campaigns where there's a set of sites here where someone went up to Canada and specifically looked at differences in the same very near area. Okay? So the Boreas sites, 2 years of a field campaign. Get you a sense of kind of where the data is coming in. Okay? This was constructed from Excel browsing the cube. But in fact, all of the slides I'm about to do are just simple things kind of done as an artifact of having the data in the database. You can also see with this one sort of the beginnings of 2002 where you really have a lot of the data coming in. We were talking about lots of different data types. This plot's showing you all of the various data types. We've got a kind of a garbage collection, other data type that's hiding another 40 or 50 kinds here. And you can see that everybody measures soil temperature. It's easy. Everybody measures ambient temperature. It's also easy. But getting some of these other measurements is not so hard, not so good. In fact, one of the things that was interesting about this plot is when we first showed it to Dennis and Bev, and in fact, Tom Bowden at Oak Ridge, they were surprised. They said, wait a minute, there's more GPP than that. Because GPP and NEE are the two scientific quantities that people really want to do the carbon science. But lo and behold, there isn't very much of it. And they didn't actually know that because nobody had ever been able to see the data as a collection. Okay? So, yeah, that's kind of a fun little plot. Deb was talking also about different research agendas. One of the sites here in Wisconsin is an education television tower. And they're taking a lot of data because it's fun. You know, they've got a 300-foot tower. They take vertical profiles, and they're having a great time. Communal science at its finest. Anything else? Yeah, again, here you kind of see the soil temperature and the ambient temperature being the big blocks. Everybody's taken them. But very irregular reporting. Now, one of the things that we think we're enabling, or we hope to be enabling, is browsing for data quality. And the two pictures on the left are thanks to Gretchen Miller. It's a simple plot of average temperature across all reported years at each site, so each point corresponds to a given site, versus latitude and longitude. Excuse me, versus latitude. Now, you'd think when you get to the pole, it gets colder, right? So a general trend down would be a good thing. But that's not happening. Lo and behold, if you start looking at month reported and total data, so January, February, March, you find that there's not a lot of data in the colder sites in the winter. Okay? It's cold. Who wants to go to Alaska in the winter? Not me. What does that say, though, about the applicability of that data for other sciences? Essentially, you're using ambient air temperature as an indicator of the overall quantity from the tower. Okay? A simple scatter plot where you plot gaps as zeros kind of gets you a rough guess of, if you like, how well does that scatter plot make sense? Well, if I have too much data on the axes, I got too many gaps. And actually doing the comparison maybe isn't a good thing. Okay. Another browsing for data quality, we were talking about September 11th. This slide actually looks at the, what was that? It was radiation around September 11th. So that's actually half-hourly measurements. And oddly enough, one of the sites just pops out. Well, it turns out it's a site in Canada that had the error of reporting their data in GMT instead of local time. Okay? So you see these kinds of time shifts. This one is also fun. This is basically two sites, 3 miles apart in California. And either there's an awful lot of funny business going on where the temperatures seem to be different by 90 days, or we got a time problem. So again, browsing for quality. Fahrenheit, I love global warming. This is real data reported by real people. It's been through the quality procedures at Oak Ridge, and we're still popping things like that. So
what is that upper right plot mean? I'm really having a hard time.
the upper right, what that is just maximum air temperature across the various years across sites. And this should be degrees Celsius. 80 degrees Celsius is pretty warm. They're reporting it in Fahrenheit. Okay? They're reporting Fahrenheit. It happens. Right? But when you look at the data itself, it looks fine. You know, you see these nice diurnal patterns, everything looks good. When you look at when comparing with something else, this one looks fine by itself. This one looks fine by itself. Compare the two, and there's a problem. So being able to look across site is actually making the data from each site better. Okay. So what have we learned so far? Well, I think the first thing we learned was that the metadata, the stuff like climate, leaf area index, is as important as the data. There's an awful lot of attention these days being looked at in terms of this web download and things like that. In fact, there was a wonderful Quashie study that looked at the most commonly downloaded data in environmental science, and that was information from stream gauges. Well, that's really great, but the first thing, or at least one of the things that you need to know before you use that data is there a dam upstream? If there is, that's metadata. Okay? And it's not necessarily available with the data. So the two need to travel together. The two need to be curated together. Controlled vocabularies are hard. You know, we've picked up well over 1,000 unique column headings at this point. And we've worked with the Oak Ridge folks and sorted through the various naming conventions. We've found a good overlap of about 30. A very nice example is the GPP measurement. Again, what they're really interested in doing, gross ecosystem production. It's reported as GPP, GEP, and GEE. Scientists know the difference. Computers don't. We've had to assume that there's going to be a decode in the pipeline. Okay? And that decode will be changing every time we do a download. It'll always require a certain amount of feedback. I went around and new to databases, I went around and I asked everybody, so I'm going to put this stuff in the database, like, what should the schema look like? Well, everybody I talked to had an opinion, okay? And I talked to SQL people, I talked to XML people, they all had an opinion. And there were basically three different sort of families. There was the put everything with a single value and make a really tall table, put everything in a really wide table, and then the one that was in between, okay? That's sort of a fractal table. Everybody I talked to told me exactly why that was best. Everybody told me exactly why the other one was wrong. And the answer is, there's no good answer. Right? What we've ended up kind of learning is that really we build a class of mechanical programming to go between, okay? And use the right one for the right job. It's just, there's no right answer. Database guys, there's a whole database literature about this, by the way, and it turns out that some of the people tell you that they have an answer, and some of the people occasionally tell you that there's no answer. Visual programming tools are really great for prototyping. We started, there's a whole lot of tools around SQL Server now. Being able to import and export data simply by drag and drop, being able to make some of the plots, server-side rendering by drag and drop. They're really fascinating because they're great for prototyping, but debugging is horrible, right? When something goes wrong, you have no idea. And that's kind of a really interesting sort of question, I think, from a computer science point of view, because the ability to drag and drop from an end user like me who doesn't really want to code is terrific. But when something goes wrong, I'm going to stop using the tool. So again, kind of an interesting little thing. And data analysis and data cleaning are intertwined. I don't think we knew that when we started either, that you end up doing the same sorts of things, those plots that I showed you earlier about sort of the time series plots. You draw the same plot when you're doing science or doing data cleaning, and they're intertwined. Being able to share the same tools and visualization seems really, really kind of interesting, again, because it's that familiarity, being able to use the tool so you're able to look at the data, not the tool. I'm going to turn it back to Deb now for the wrap.
Okay, so what we wanted to do is now that you've heard about the data server and sort of where it is now, I want to give you a quick overview of sort of where we're headed now and some of the research goals that are left in place. And obviously we need to improve our current capabilities. Right now what we have is largely a prototype, fairly fragile. A lot of issues left to do. The other aspect is we're just starting to receive the gap-filled data of all of this same data. There's a European group that has a gap-filling algorithm. They're shipping all the data to the European group. It's then coming back. There'll be a second set of data that's all of the same data but gap-filled. And Catherine already talked a little bit about that. We really, we need to implement a lot of the data staging stuff so that the scientists can edit their data and so that we can ingest the new data as it keeps appearing on the Ameriflex site, in a very automated way. Right? This should be something that just happens in the background and we don't have to think about. And that scientists, when they want to change the calibration or change some of the data, can just ask for the particular data, make the changes in the flat file, and ask for it to go back up to the site. There shouldn't have to be a human involved very much in this process from our side, from the data server side. Most of the others are pretty straightforward. We're gonna take advantage of another one of the SQL Server tools. There's a reporting services that actually can do a lot of the database mining of things that we already know you want to know about the data. We can create reports that'll just automatically create web pages and put up reports about the data. I think that'll be really nice for the scientists to be able to, have some standard things that they can just browse through and have already pre-generated about the data. The next big thing for us is really starting to apply this in the water arena and start to work with a regional water problem and use water data. So we're talking currently to the Russian River or some Yosemite Valley folks at UC Merced. There's also been some discussions with the Salinas Valley. And we need to automate things. We need to get better at some of the spatial GIS issues. We're going to work with Maggie Kelly on some of those. She's here at UC Berkeley. And we need to link to the imagery data. Again, that's Maggie Kelly's area, and she'll be working with us on that. Longer term, as I already mentioned, we need to handle the imagery data. We need to be able to have that be a natural component of the system. It turns out that there's a lot of calculations that the scientists want to be able to have happen standard on the data. It doesn't make sense for them to have to gather the data out of the data server, do those calculations every time, right? The data server ought to be able to just have the standard calculations already in the system, be able to create that data in advance. As Catherine mentioned, these scientists have already their favorite statistical package. It ought to be fairly trivial for them to be able to connect to them. They ought to be able to link in their models and do the data mining. Here this is sort of a more longer, much longer term thing, largely a research issue. But in the ideal case, I ought to be able to just subscribe to particular events, right? Be able to say, if you ever see a spring that's more than X amount of rain, notify me so I can go grab that data, right? I mean, long term, you ought to be able to just launch these sort of mining subscriptions and have the data just have things notify you when it finds data that matches those criteria. Right? We can do that today for web pages. We can't do that for data very well. We ought to be able to. We also ought to be able to support in the long term, but again, another longer term research project, so that the scientists can actually put together a workflow and say, these are all the things that I need to have happen to the data, right? In the whole staged process, rather than have to step the data through themselves manually. So in conclusion, we're almost out of time as well, so I'll try to make this very fast. But really, we've got these large data archives. Hopefully, I've convinced you that that is not the be-all and end-all of what I need to do science at this point. It just opens that door. And that these small collaborations are where that science is going on, the regional scale, the global scale science, at least in the life sciences, and they need a lot of help. And I think this data server is really an attempt on our part to start to look at what are the tools they need to really enable their analyses and their capabilities. And the last point is really critical. It's really easy for us as computer scientists to look at the problem and say, we know what you need, and go off and build the monstrosity, right, that does everything that every computer scientist ever wanted to do, right? The beautiful metadata capabilities, all these things. But the reality is, it's all about enabling the scientists. And that's been our other focus, is really trying to keep ourselves reined in and not do too many of the really fun computer science things that would send us off in a divergent track, and really stick with, will it enable the science? Will it enable these guys in a dramatic way? If it will, let's do it. And so that's the other key. And with that, I'd like to end the talk and put up some URLs for people and invite any questions for either of us.
A round of applause. Kevin and Catherine, thank you very much. We just have time for one burning question, I think, before the students rush off. I should have used the microphone. Is there one burning question? Of course, they're going to stay for a while, and you can come and talk with them as well. Jane, make it quick.
So if you look at the computer scientific contribution is using database and data mining for this scientific problem. So do you have other computer scientific contribution other than real instantiation of the database?
Actually, there are a couple of things, if I may.
No, go ahead.
We have to keep it short. Sorry to be pushy.
Using commercial tools is certainly the crux of our actual use. Dealing with some of the security interactions with grid security is one. I mentioned Tableau, I think, earlier. That's a case where data visualization research is actively going on, and we're just leveraging it.
But I think also, what you've seen right now is the first stages, which is just get the mechanics in place. And a lot of the computer science research is, we've just set the stage for now.
Yeah, the what ifs, find me data that looks like.
Yeah.
Okay.
Why don't I invite others to come up and talk with them privately at the end of our seminar? And once again, thank you very much. It was really interesting.